Hello everyone, in this video we are going to discuss about the encoder. In the previous video we have discussed about the combinational circuits and half adder, full adder, half subtractor and full subtractor. In this video we are going to discuss about the encoder. There are two more combinational circuits called encoder and decoder. Generally encoder is used in the transmitter side and decoder is used in the receiver side. The input message signal is encoded using the encoder and transmitted along the channel. The receiver side, to get the original input message, the decoder is used to decode the encoded message. The encoder has an input of 2 power n input line and n output line. From this 2 power n input line, n bit output will be generated, which means 2 power n bit input message is encoded into n bit output message. The output is a binary code which is equivalent to the input, which is active high. The output binary code is equivalent to the input, which is active high. For example, if y1 is active high, then the binary output is equal to the binary equivalent of this suffix 1, which is nothing but 0 1. The output will be equal to the 0 1. If the input y3 is high, then the output will be equal to the binary equivalent of this 3, which is nothing but 1 1. Okay, that is, the binary code equivalent to the input is produced as an output, which is active high. The encoder encodes 2 power n input line with n bits. There is one more signal called enable signal, which is optional. If the enable signal is high only, the encoder will operate. If the enable signal is low, the encoder signal will not even operate. The first encoder is 4:2 encoder, which means it has 4 input lines and 2 output lines. This 4 could be denoted as 2 power 2. The value of n is 2. So 2 power 2 is to 2. There are 4 input lines and 2 output lines. This is the truth table of an 4:2 encoder. 4 inputs y3, y2, y1 and y0 and 2 outputs a0 and a1. For this 4:2 encoder, there is an assumption that at least one of the input should be high. If all the input are 0, then the output is wrong. The output is an ambiguous output. The produced output when all the input are 0 is invalid. And the next assumption is only one input should be high. Only one input should be high at the same time. Not more than one input should be high at the same time. For this first combination 0001, y0 is high, so the output is nothing but the binary equivalent of the suffix 0 0 0. For second combination, y1 is high, so the output is nothing but the binary equivalent of this 1 0 1. The binary equivalent of 1 is 0 1. The next combination, y2 is high, so the output is equal to the binary equivalent of 2, which is nothing but 1 0. And in the next case, y3 is high, so the output is nothing but the binary equivalent of 3, which is 1 1. Next, we need to generate the Boolean expression for these two outputs a0 and a1. a1 is high when y2 is high and y3 is high. So y2 plus y3. a0 is high when y1 is high and y3 is high. So a0 equal to y3 plus y1. These two are the Boolean expression for the two outputs of 4:2 encoder. This is the logic diagram for 4:2 encoder. A1 is obtained by using this OR gate, and for this OR gate y3 is applied as an input and y2 is applied as the another input, and this OR gate is used to generate A0. The input for this OR gate is y3 plus y1. These two are given as input for OR gate, and the output of this OR gate is nothing but A0. This is all about 4:2 encoder, and there is another encoder called octal to binary encoder. Octal means 8. 8 could be represented as 2 power 3. Here the value of n is equal to 3. So 2 power 3 is to 3. It has 3 output lines, 8 input lines and 3 output lines. This 8-bit input signal is encoded into 3-bit output signal. This is called octal to binary encoder. This is the truth table for octal to binary encoder. Similar to 4:2 encoder, the octal to binary encoder also works in the same way. The output is nothing but the binary equivalent of the input, which is active high. Here y0 is high, so the output is equal to the binary equivalent of 0. In the next case, y1 is high, so the output is equal to the binary equivalent of 1, which is nothing but 0, 0, 1. Let us take the last case, that is y7 is 1. The y7 input is 1, so the output is equal to the binary equivalent of 7, which is nothing but 1, 1, 1. This is the case for octal to binary encoder. For 4:2 encoder, we have assumed two cases, that is, at least one input should be high and not more than one input should be high at the given time. These two assumptions also applicable for 8:2 encoder, that is octal to binary encoder. These two assumptions are also applicable for octal to binary encoder. Now we need to generate a Boolean expression for these three output value A0, A1 and A2. A2 is high when Y4, Y5, Y6 and Y7 are high. Y4, Y5, Y6 and Y7 are high. A1 is high when Y2, Y3, then Y6 and Y7. So Y2 plus Y3 plus Y6 and Y7. When any of these one input is high, A1 will be high. Then A0 is high when Y1 is high, Y3 is high, Y5 is high and Y7 is high. So A0 equal to Y7 plus Y5 plus Y3 plus Y1. If any one of these input is high, then A0 will be equal to 1. So from these three Boolean expressions, we could construct the octal to binary encoder using logic gates. To generate A2, we are using this OR gate. This is 4 input OR gate. The 4 inputs are Y4, Y5, Y6 and Y7. The A2 is generated by using Y4, Y5, Y6 and Y7. So for this OR gate, the inputs are Y4, Y5, Y6 and Y7. The output of this OR gate is A1. A1 is resulted from Y7, Y6, Y3, Y2. So the input for this OR gate is Y7, Y6, Y5, Y3 and Y2. Sorry, not Y5. Y7, Y6, Y3 and Y2. And the output of this OR gate is A0. And the input for this OR gate is Y7, Y5, Y3 and Y1. Thus the three outputs are produced for this octal to binary encoder. We have seen two disadvantages. And to overcome these two disadvantages, priority encoder will be used. The first disadvantage, as I have already mentioned, when all the inputs of the encoder are 0, the result is ambiguity. The result will be invalid. If more than one input is active high, then the encoder produces a wrong output. The output produced by the encoder when more than one input is high could be wrong. It may be wrong. It could also be correct, but the probability of being wrong is high. To overcome those two disadvantages, priority encoder is used. In priority encoder, the priority will be set to the inputs. Consider there are 4 inputs, Y3, Y2, Y1 and Y0. The highest priority will be given to Y1 and the next priority to Y2, next to Y1 and the least priority will be given to Y0. The least priority will be given to Y0. There are two outputs, A1 and A0. In this case also, at least any one of these input must be 1. At least any one of these input must be 1, and there could be more input that has a value 1. If at least one input of the encoder is 1, then the code available at the output is valid. At least one input should be 1, then the code is valid. If not, the code is invalid. If all the input of the encoder are 0, then the code is not a valid one. In this priority encoder, more than 2 input could be active high at the same time. This is the truth table for priority encoder. When all the first case is all the input are 0, so the output is not valid. The valid bit is used in priority encoder. The output, sorry, not valid. This valid bit denotes that valid bit 0 denotes that the produced output is not valid. The next combination is 0001, y naught is equal to 1, so the output is valid. At least one of the bit is 1, so the output is valid, and the output is nothing but the binary equivalent of 0, which is 00. In the next case, y1 is 1, and this x denotes that the value of x could be either 0 or 1. If it is 0, there is no problem. Only one input is high, which is y1, and the output is equal to the binary equivalent of 1, which is 0, 1. Even when the value of x is 1, consider the value of x as 1. There are two input which has an active high at the same time, but the input which has the highest priority, in this case y1 has the highest priority, so the output will be equal to the binary equivalent of 1 based on the priority. Since y1 has higher priority than y0, the output will be equal to the binary equivalent of this 1. Next, y2 is 1 and y1 and y0 are x. If the value of x are 0, then there is no problem, only one input is high, which is nothing but y2, so the output is equal to the binary equivalent of 2. Even if this value of x is 1, consider these two values are 1, there are more than one input as an active high at the same time, but based on the priority, y2 has the highest priority, so the output is equal to the binary equivalent of 2, which is nothing but 1, 1. Similar for the case y3. Since y3 has the highest priority, irrespective of the lowest priority bits, the output is equal to the binary equivalent of this 3, which is nothing but 1, 1. If the highest priority bit is 1, then irrespective of the lowest priority bit, the output will be set to the highest priority. Now we need to generate the Boolean expression for these three outputs, A1, A0 and V. A1 is high when Y2 and Y3 are high, so Y3 plus Y2. A0 is high when Y3 is high. A0 is high when Y3 is high, so Y3, and A0 is high when Y2 is 0 and Y1 is 1. Y2 bar which denotes 0 and Y1. This is the expression for A0. A0 is high when Y2 is 0 and Y1 is 1. So Y2 bar Y1. The valid bit is 1 when Y0 is 1, Y1 is 1, Y2 is 1 and Y3 is 1. So valid bit equal to Y1 plus Y2 plus Y3 plus Y4. This is the expression for the valid bit. Using these three Boolean expressions, we could construct priority encoder. This is the logic diagram of priority encoder. This OR gate is used to generate Y3 plus Y2, which is nothing but Y1. This OR gate is used to generate A0, which is nothing but Y3. Y3 is given as one input for this OR gate. And to generate Y2 plus Y2 bar Y1, NOT gate is used to generate Y2 bar, and to multiply it with Y1, we are using this AND gate. Using this AND gate, we are generating Y2 bar Y1, which is given as an input for the OR gate. The output of this OR gate is nothing but A0. To generate V, we are using one more OR gate. The input for this OR gate is Y0, Y1, Y2 and Y3, and the output of this OR gate is nothing but V. Thus, we have realized the priority encoder using logic gates. Thank you.